Monday, but it's a good place to get started, right? So we've talked about acids and bases. We've done a titration with them in lab, right? Acids and bases are usually involved in which type of the chemical reactions we talked about before? If you mix an acid and a base together, what kind of reaction would that be? Neutralization, right? Because it generates water and salt, right? It makes something that's, we think acids and bases, something that are very reactive, corrosive, toxic, but if we mix them together, they form water and salt, something that we can think is neutral, won't affect us very much. And so acids and bases have a couple different definitions. So there are what we call Arrhenius acids and bases. These are acids are defined as something that make hydronium in aqueous solutions. And hydronium is just going to be H3O plus is how we define it. It's an ion in aqueous solutions. You'll see people use hydronium and H plus interchangeably. That's because an aqueous solution means what kind of solution? Yeah, dissolved in, it usually means water, right? Aqueous means that you have a solution made up of water molecules, right? So if you have something like hydrochloric acid, HCl, and you mix it with water, what the acid reaction does is we take something water's in its liquid state, is it creates an H3O plus ion, which is H3O plus. And this ion is how we define acidity, right? So that ion determines how we define acidity. And the other product we have here, we have left over, is just a chlorine ion, right? We see that the charge on both sides of this reaction is conserved. This is what we would call our acid reaction. So when you put an acid into water, it's not that acid that's doing directly the reacting. You're generating H3O plus, and H3O plus is what is involved in chemical reactions, right? Because that's an extra hydrogen there. It's eager to get rid of that hydrogen when chemical reactions. That means it's likely to reduce things, give away a proton. Right, so it generates H3O plus, which is called hydronium, or it's commonly written that when you put this into solution, you just get an H plus and a Cl minus. Right, H plus is used interchangeably, right? This is used the same way H3O plus is used. Right, so if you see people say protons, hydrogen, donation of hydrogen, or hydronium, those are all used the same way. Does that make sense? Right, so an acid is anything that'll generate H3O plus in solution. That's how the Arrhenius definition is concerned, right? All that matters is do we generate H3O plus or not? If we have an Arrhenius base, right? Bases don't deal with the generation of H3O plus. They deal with the opposite. So water is a special type of material because it can accept a proton or get rid of one. Bases deal with anything that makes hydroxide in solution, right? So that's OH minus, right? And we know hydroxide because it's a polyatomic ion. And so there's generally two mechanisms, right? So in the first one, it's easy to see that the proton is donated to water. There's two mechanisms for generation of OH minus in solution. If we have a strong base, we'll talk about what those mean in a bit. A strong base, something like sodium hydroxide. If we dissolve that, put it in water, it becomes Na plus aqueous plus OH minus aqueous, right? The polyatomic ion is ionically bonded to sodium, and it makes this hydroxide ion, which is how we define it as a base, in accordance with the Arrhenius definition. If we have something that is considered a weak base, and again, we'll talk more about what those mean, something like ammonia, NH3, in solution, and we put it in water, right? So notice that the first strong base doesn't really require water. What happens is the weak base takes a proton away from the water, right? So this one of these protons is going to go onto that weak base to make NH4 plus. Does anyone remember what that ion was called, that polyatomic ion? Ammonium. Yeah, that was ammonium. And the byproduct of that, when we take a proton away from the water, is we get hydroxide. Right? So both of these are considered Arrhenius bases because they generate OH minus in solution. And what we'll learn about acids and bases is acidity and basicity all depends on this hydroxide or hydronium concentration, and you can always look at it from either point of view. What is the concentration of OH minus, or what is the concentration of H3O plus or H plus in solution? And both of those will tell you if the solution is basic or if it is acidic. That's how we define an Arrhenius acid and base. Right, so there's a couple different definitions for acids and bases because, as time went on, chemists found that, okay, well, we can have these things that don't traditionally fit into our classic definitions that do act like acids and bases. All right, am I good to go on? Anyone still writing? All right, so then a guy named Bronsted and Lowry, they came up with definitions of acid and base. Said, well, it's not just if it makes H0 plus or OH minus in solution. It has to do more with the proton movement, meaning what's happening to this hydrogen in solution when we add this compound. And so an acid is considered a proton donor. And when I say proton and hydrogen are used interchangeably. Because if we just donate a hydrogen without its electron, right, a hydrogen atom has an atomic mass of 1, which means all it is just a proton. That's why protons and hydrogen are used interchangeably, right? So an acid is a proton donor, and a base is a proton acceptor, right? So for an acid, right, the same reaction that we had before, we can use, actually let's use a different acid just so we can get experience. So we can have acetic acid, which is what you guys used on last Wednesday. Right, acetic acid, this is acetic acid. It can donate a proton to water to then make, right, it donates a proton to water to make hydronium in solution. H3CO O minus aqueous plus H3O plus, right? So this definition says it's not just about making H3O plus in solution, it's the act of donating a proton that makes something acidic. And a base is going to be a proton acceptor. So if we have something like ammonia, like we just had on the previous page, in that, we put in a solution, an aqueous solution or a solution of water. That will become NH4 because it's a proton acceptor. And it creates OH minus in solution, right? So this one now accepts a proton from water, which means it's a Bronsted-Lowry base. And so Bronsted-Lowry says, okay, well, it's not just, again, OH minus or H3O plus that determines if something is acidic or basic. It's whether or not it donates a proton. So this expands the definition a little bit of especially bases. And it gives rise to what we call conjugate acid and base pairs. Right? So we can have something that originally donates a proton. What's left over is something that accepts a proton. And so these are called conjugate acid-base pairs. So let's look at the example of acetic acid that we had previously, HCOOH, aqueous, plus H2O goes to H3COO minus aqueous plus H3O plus. Initially, our acetic acid, right? This is something that donates a proton, right? So we classify that as an acid because of that, right? We classify this, let me use a different color, we classify this as an acid because it's a proton donor. We notice for the reaction here, and for all acid-base reactions, that the reaction arrow is these two half arrows going in either direction. Does anyone know what that means? Or anyone remember what that means? Yeah, this reaction goes forward and reverse. It means there's an equilibrium associated with this, meaning that eventually you reach a point where the reaction stops making more products and stops making more reactants, meaning the reaction is still going on, but the concentrations of everything on both sides stay the same. Right? That's what it means when we're in an equilibrium. And so since this reaction can go both directions, it means that after acetic acid donates its proton, what's left over is called acetate, right? This thing can accept a proton now, right? It has this negative charge, it can accept a proton. If something accepts a proton, how do we define that? Is it an acid or a base? It's a base, right? So now this is what we call a conjugate base because it accepts protons. Since this reaction can go both directions, if we're going in the opposite direction, it's like the water or the hydronium donates a proton to the acetate to then make acetic acid, right? That's what the reverse reaction looks like. And so we call it conjugate base because it acts as a base, but it's derived from the acid that we started with, right? So we start from acetic acid, we donate a proton, which makes it acidic, and what's left over is called acetate, and that compound can accept protons. So it acts as a base, and its conjugate comes from acetic acid. All right, so in this case, what does water act like on the reactant side, going in the forward direction for this reaction? It acts like a base, right? So this acts like a base because it's a proton acceptor. And that means that hydronium wouldn't be its conjugate base, it would be called its conjugate what? It would be its conjugate acid, right? Because after water has accepted a proton to become hydronium, going in the reverse direction, this hydronium would donate a proton to the acetate. If it's a proton donor, that's defined as what? An acid, right? So that becomes the conjugate acid of acetic acid, of the water. So this would be the conjugate acid. All right, because it's a proton donor when the reaction is going in the opposite direction. And so which one you call the acid, which one you call the base, it doesn't really matter, just depends on which way you draw the reaction, right? If I drew this reaction in the reverse order, then I would call hydronium the acid, and I'd call acetate the base. Acetic acid would then be the conjugate acid, and then water would be the conjugate base. All right, so let's get some practice doing that. Here, we have water, chlorine ions, and hydroxide involved in this reaction. So to determine whether it's an acid or a base, we're looking at the donation or accepting of what? Protons, right? So originally, where do the protons come from on the reactant side? or which molecule has the protons in it, or the hydrogens, right? Protons, hydrogens, they're going to be used interchangeably all the time with acids and bases. All right, if we had to plot the movement of protons or hydrogen in this reaction, what's donating protons and what's losing protons? Or what's accepting protons? Yep, chlorine is accepting proton, right? This proton right here, one of them gets donated to the chlorine, right? And when that happens, so how is water defined here? An acid, right? Because it's donating a proton. This is donating proton or hydrogen. Again, those are interchangeable here. So this makes this an acid. Chlorine is doing what? Accepting a proton, which makes it a base. Which means HCl is going to be what? Is it going to be the conjugate acid or the conjugate base here? And you say, well, I don't know right away because they flip the orders of these things. If you're going in the opposite direction, like pretend this reaction is flipped the other way. So I'm just going to write it down here. OH minus plus HCl goes to H2O plus Cl minus, right? This is just the same reaction, just written in the opposite order, right? What is OH minus here doing? Is it accepting a proton or is it donating one? It's accepting one, right? It's taking this proton to become H2O, which is what's happening in the above opposite reaction. This one accepts a proton to then regenerate H2O. But this comes from the water molecule originally, right? But because it acts like a base going in the opposite direction, this was our acid originally. This should be our conjugate what? Conjugate base, right? Because it's accepting a proton, right? OH minus can accept a proton from something because it accepts a proton going in the opposite direction, which means that HCl is what? Conjugate acid. Right, so that's our conjugate acid. Because it donates protons. And we can visualize that just by looking at the reverse reaction, right? OH minus plus HCl, you can identify what's accepting, what's donating a proton, but we know these are derived from their originals on the other side, so that's why they're the conjugate of whatever it is, right? Our conjugate acid comes from our original base. Our conjugate base comes from our original acid. And again, that just depends on which way you write the reaction. You also notice something in this problem, right? We see that H2O acts as an acid, right? In this one, H2O act like what? A base. So there are materials and compounds that act as both, and those are called amphoteric materials. So water is what's called an amphoteric material. They can act as both acids and bases. So that's just a side note. Amphoteric compounds. These act as acids or bases. And this idea of water being amphoteric is ultimately what leads to how we define if something is acidic or basic. Does anyone know how do we define if something is acidic or basic? What scale do we use? pH, right? And this ability of water to act as both is how we're going to define the pH scale, which tells us if something is acidic or basic. Because water can generate hydroxide or hydronium, and if it generates a lot of one, that means it's going to take away from the other. And so you're going to get these two scales that are going to be opposite to each other. And we'll finish up talking about that on Monday. So there's another problem that talks about conjugate acids and bases here. I actually have a number of practice problems related to that, so it's good to be able to do that. And there's actually one last definition of an acid or a base that I'll go over on Monday, which will be a Lewis acid or a Lewis base. And so all of those are going to be, instead of looking at movement of protons, we're going to look at the donation or the accepting of lone pair electrons. And the reason for this is it expands the definition of acids by quite a bit, not bases really much, because if you put highly charged small metals in water, they can accept lone pairs from water to then generate H3O plus or OH minus in solution. So it expands the definition of what can be an acid by quite a bit. All right, so we'll take a break. We'll head up to lab.